When you envision robotics, the sight of hefty price tags might be the first thing to cross your mind. But what if I told you access to the cutting edge doesn't have to break the bank? What if the forefront of innovation was available for less than you might think? My name is Jacob Stieneker, and I'm currently working on my student innovation project for the University of Advancing Technology. As a robotics major, I decided to create a 3D printed robotic gripper solution that connects directly to the Universal Robots tool bracket. While the 3D model is unique, the innovation lies with this being the only 3D printed solution that I've come across that can not only directly interact with the Universal Robots onboard I/O, but also be programmed in the robot's native language without needing a microcontroller. The whole idea behind this was to simplify things not only for the robot, but also the operator. So let's get into it. The physical design of the gripper was the first step in the process and arguably the most difficult for me. I decided to go with a 3D printed solution because it's cost effective and it's a lower payload for the robot. Plus, in the amount of time it takes to order and wait for your end-of-arm tooling to be shipped to you, you could print and assemble your gripper solution in half the time. I also faced challenges in the 3D modeling process when it came to calculating the proper gear ratio for the gear-driven components, stress testing parts to see what density they needed to be printed at. I did add an offset so the robot could operate in food grade applications because the robot itself is not food grade. So one way around that would be to print an offset using a food grade material to where the robot never has to operate directly above the food. I think I went through about 3 different motor types before I landed on the solution that was going to work for this project. My initial thought was to use a servo motor, but I found myself trying to get the servo to operate more like a DC motor, and I realized I didn't really require position feedback. So I ended up disassembling like 3 servo motors, trying to get them to work the way I wanted, and it ended up just not working out. So then I moved to a standard DC motor and determined it was just too big and too fast for what I needed it for. But I landed nicely on a 12-volt worm motor that rotates at 25 RPMs, and it seemed to do the trick. It's a lot safer too because it rotates a lot slower and it stalls out before it risks breaking the 3D printed fingers. Plus, it never exceeds the robot's tool current specs even when it's stalled out. Now, after finding the right motor, I had to find a way to operate that motor in forward and reverse without using a microcontroller, which was extremely difficult. I ended up finding a 12-volt forward-reverse relay module that worked great for this. With the relay module, the robot operates the gripper using a 12-volt NPN signal, meaning the robot is providing a constant 12-volt signal for power, but sends an intermittent 0-volt signal when I want to operate the gripper. The entire assembly with all of the components ended up being 10.4 ounces, which is a lot lighter than I expected. I was able to successfully write code on the robot side that operated the gripper seamlessly within a program. That was the easy part. I wanted to take it a step further. So the robot has an interpreter socket which is used to program it externally from a computer in any language you want. That was my next goal, to make this gripper programmable in any language. I tested this first using Python. I first had to establish connection between the PC and the robot, and then all I had to do was I wrote code for the interpreter socket on the robot side, and then wrote some commands down in a text file for the Python program to read, and sent them to the robot. Finally, I ran the code from the PC and watched the gripper operate through Python, which was really exciting. As a final test for my gripper solution, I programmed the robot to perform a small-scale palletizing application. So let's take a look at that. So there you have it, a 3D printed robotic gripper solution. Let's recap on the innovation highlights for this solution. Lower cost, lower payload, lower power requirements, qualifies for food grade applications, connects directly to the Universal Robots tool bracket, no microcontroller needed, the ability to be programmed in any language. With all of those features, this gripper provides you the ability to grasp the future for less. I'm Jacob Stieneker, and this has been my student innovation project.